In mathematics, a random walk is a random process that describes a path that consists of a succession of random steps on some mathematical space, 2D or 3D. An elementary example of a random walk is a random walk on the integer number line z, which starts at 0 and at each step moves +1 or -1 with equal probability. Random walks have applications to engineering and many scientific fields, including ecology, psychology, computer science, physics, chemistry, biology, economics, and sociology. The term random walk was first introduced by Carl Pearson in 1905. A popular random walk model is that of a random walk on a regular lattice, where at each step the location jumps to another site according to some probability distribution. In a simple random walk, the location can only jump to neighboring sites of the lattice, forming a lattice path. In a simple symmetric random walk on a locally finite lattice, the probabilities of the location jumping to each one of its immediate neighbors are the same. The best studied example is of random walk on the two-dimensional integer lattice, sometimes called a hypercubic lattice. An elementary example of a random walk is a random walk on the integer number line z, which starts at 0 and at each step moves +1 or -1 with equal probability. This walk can be illustrated as follows. A marker is placed at 0 on the number line, and a fair coin is flipped. If it lands on heads, the marker is moved 1 unit to the right. If it lands on tails, the marker is moved 1 unit to the left. After 5 flips, the marker could now be on -5, -3, -1, 1 through or 5. With 5 flips, 3 heads and 2 tails, in any order, it would land on 1. There are 10 ways of landing on 1 by flipping 3 heads and 2 tails. 10 ways of landing on -1 by flipping 3 tails and 2 heads. 5 ways of landing on 3 by flipping 4 heads and 1 tail. 5 ways of landing on -3 by flipping 4 tails and 1 head. 1 way of landing on 5 by flipping 5 heads, and 1 way of landing on -5 by flipping 5 tails. Let's look at the figure for an illustration of the possible outcomes of 5 flips. Let's take a look at a random walk in 2 dimensions. And another example of a random walk in 2 dimensions with 25,000 steps. To apply the logic of the random walk in music, let's imagine starting at one particular note, let's say the middle C, and by applying a random walk with a maximum step of 1, decide to create a sequence of notes. The step 1, since now we will be dealing with the chromatic scale, will be 1 semitone. So, by beginning at C, we have 3 options that all have the same probability. A step of 1 semitone higher, of -1, 1 semitone lower, or 0, meaning staying where you are, so repeating the same note. So from C, we can go to C sharp, B, or stay at C. From C sharp, we can go +1, -1, or 0, so D, C, or C sharp. Let's go with D. From B, we can also go +1, -1, or 0, so C, A sharp, or B. Let's go with B. And from C, we can go +1, -1, or 0. So C sharp, B, or C. Let's go with C sharp. Let's just say that for the upper line, we generate at random the following sequence. For the medium line, we generate at random the following sequence. And for the lower line, we generate at random the following sequence. One parameter that defines a random walk is the size of the maximum step allowed. A random walk having a step size that varies according to a normal distribution is used as a model for real-world time series data such as financial markets. It is called a Gaussian random walk. In the previous examples, the maximum step was ±1. Let's now generate a random sequence with a maximum allowed step of ±2, meaning that the possible steps from any given note are a whole tone up, which is a +2, a semitone up, +1, repeating the note, step 0, a semitone down, -1, and a whole tone down, -2. For the time being, we are sticking with a chromatic scale, but later on we will also show other possibilities. Let's now generate a line using a maximum step of ±2 for the upper line, starting where the previous line ended. Let's now generate a line using a maximum step of ±2 for the middle line, starting where the previous line ended. And let's now generate a line using a maximum step of ±2 for the lower line, starting where the previous line ended. As an exercise now, I'm inviting you to write 3 different lines of 48 notes each, starting at C4, all of them based on random walks with a maximum step of ±3, meaning a minor third. Since I am asking you to apply it based on the chromatic scale, as we did in the previous examples, the intervals you are allowed to use would thus be a minor third up +3, a whole tone up +2, a semitone up +1, repeating the note, step 0, a semitone down -1, a whole tone down -2, and a minor third down -3. I suggest you proceed as follows. Write down your random sequence, first writing the numbers without plus or minus signs. Then write down the plus and the minus signs in front of the numbers without thinking about it too much. Try to make it as random as possible. Do not try to think about it musically. Do not have any intention behind your numbers. You can also use the following website to generate your numbers, entering the maximum steps each time. We're now going to combine the random walks and the sieves we saw earlier on in order to understand that the random walk can be applied on any given musical material, a scale, a mode, a sieve. So, if we take the same random walk, the same sequence we used earlier, the one with maximum steps of ±2, and apply it on the sieve we prepared earlier, starting at C4, it will give us the following result. As you can see, now the step ±1 or ±2 refers to the available notes of the sieves we have, do not necessarily correspond to semitones or whole tones. In this case, ±1 means moving up or down by one step, playing the next or the previous note, no matter what the interval is. Consequently, ±2 means moving up or down by 2 steps, no matter what the interval is. +2 from the middle C4 is D sharp, -2 from the middle C4, G sharp, and so on. If we take the same random walk and we apply it at a different starting point, the horizontal line will sound relatively different, since the available intervals will create different melodic relations. As an exercise, I now ask you to apply the random walk you wrote for the previous exercise and apply it on your sieve, starting at 3 different points, paying attention to how the same walk can create different melodies while staying faithful to the overall contour.